All right. Oh, yeah. Yes, actually, I'm full professor now. I'm also chair of the Department of Geography at UVic. My specialty, research specialty, is weather and climate. My main area of focus is the Arctic. I've been up there since my first field season in 1990, in 4 months in a Logan tent in central Ellesmere Island. Right now I work on basically how does weather affect what you're doing? And so we work in Indigenous communities. I used to be at the University of Alaska Fairbanks in the Atmosphere Science Department. Same question. So working with Alaska Indigenous communities, Canadian Indigenous communities in the Western Arctic, Coast Guard, heavy shipping operations. When I was in the States with NOAA, National Oceanic and Atmospheric Administration, the Pacific Services Center out of Honolulu, we worked on Pacific issues as well. Along this line, I've got students and projects that do work in the field. So like I say, we go to the Arctic, we work with communities. I also set up weather stations on glaciers like Columbia Ice Field and the Hani Ice Field. But then I've got projects that just focus on more theoretical aspects like storms. So I've had students who've done a fair bit of work with storms, tracks, different ways to think about a storm. And if you think about it, everyone knows what a storm is. I'd probably jumping the gun, but everyone knows what a storm is. And so until you tell the computer to go find storms in pressure data, then you have to say, okay, well, it's a pressure drop of such and such, and the storm must be so wide and all this kind of thing. It becomes a bit of a challenge to actually define specifically what a storm is. And if you think about, say, the harbor master over at Vancouver or something like that, for them a storm is something that brings strong winds, heavy waves, and is disruptive to the boats in the harbor. If you're the person who manages the stormwater system in Vancouver, you don't really care if it's windy. You care if you get 50 millimeters of rain in a 2-hour period that overwhelms the stormwater system. Conversely, the harbor master probably doesn't care if it's raining in particular. So a storm can present quite differently depending on your operational context. And this is why we hear a lot of, oh, this storm exceeded the 1 in 50 year or the 1 in 100 year event. We kind of hear that a lot. But you can get that with winds, you can get that with precip. So there are different ways to get that. Okay, well, oops.
Oh, sorry, that was on mine. This is the talking iPad 133, is that from my computer or yours?
There's a machine here.
It's because this is getting the audio, I think. Have you got your audio on here?
No, but they're picking it up on Zoom. So
okay.
Yeah.
Leave it, John. It's working. Well,
sometimes the tech takes over, it becomes an end to itself. So
okay, go ahead.
I've got Norman Shippey up here. He's one of the PhD students I had a few years ago. He now works as a consultant with a consulting firm. Now a lot of my grads go off to work in the consulting sector, actually. All right, so storms, yeah. This is just a quick look, what this is getting on about what do storms mean. In 2004 in the States, we had what they considered to be a fairly bad hurricane season. Then of course, we had Katrina in 2005. Katrina and a couple of other powerful storms, Wilma and Rita, down in the Gulf of Mexico at that time. Some of the most powerful storms, depending on what parameter you look at, that had been recorded in the Atlantic Basin, or some of the most powerful ones. And in 2004 and 2005, you get storm after storm, and you get headlines like this: no end in sight. And you think, well, we're just ramping up with these powerful storms, but then nothing right after that. So things like tropical cyclones, and we'll tease apart different types of storms here in a minute, but tropical cyclones go in waves. There are existing patterns within the atmospheric system. And of course, one of the things that we think about, we spend a lot of time with, it's not just a storm event in itself, it's what happens as a result of the storm. You know, what that we hold of interest gets damaged or wrecked. So that's another consideration. And so we can, there are a lot of research papers and so on out there that will talk about increasing damages from storms. Well, is that due to increasing storm activity, or is it due to increasing cost and amount of infrastructure in the way of storms? People really like living on the coast, and that's storm country. All right, so that's in the States, but of course, closer to home, we're no stranger to this. You know, we get storms every year of different magnitudes. Sometimes we kind of sneak through a year and they don't do all that much. Sometimes we get some fairly significant events. You know, this was back in 2010, just after I got here, actually. Had a big, what's called an atmospheric river event. We'll look at those later on. That destroyed roads. And then, of course, we had in just last fall, the really large atmospheric river event that managed to cut off Vancouver from the rest of the country for a while. You know, it severed all the road links. These are pretty significant, obviously. So in general, we've got storm damages to infrastructure on the coast through things like winds. But how else do they do that? Well, through the ocean. So storms can generate very severe marine states, big waves. And here's a picture of a ship or these two boats that look like they might not be doing so well. Is there anything, just I'll throw this out there, is there anything that you notice about these ships? That's right, yeah. Who knows this story? Someone said it's the same ship. The Selendang Ayu, it's been torn in half. This is Unalaska Island. So this is, if you know the Aleutians, this is on the north side of Unalaska Island. On the south side is Dutch Harbor, one of the largest commercial fishing ports in the US. And so this ship ran into engine problems. They shut down their engine, tried to effect a repair, weren't able to get the engine started, and got caught up in this heavy weather of the southern Bering Sea. That's typical, at this time of year, and ended up broaching and just getting torn in half. Because obviously a ship like this can't take that kind of side loading. The amount of oil spilled, there it is. And it spilled, an amount of oil, just the oil for its, or the fuel oil for its engine, 10% of what the Exxon Valdez lost. And it's not a tanker, it's just a bulk carrier. It dropped 60,000 tons of soybeans. US Coast Guard helicopter crashed during the rescue operation. It was actually hit by a wave that had broken up across the bow. So that's how poor the weather was at the time. And you'll get 3,000 ships a year trying to get through the Aleutian Islands. So it's not just on the shore with wind and rain, it's also these marine states that can affect coastal activities, but also activities on the ocean. So what is a storm? Well, basically, it's an area of low atmospheric pressure. Why is this important? Well, air moves according to pressure differences. It moves down what we would call pressure gradients. So differences in pressure, high to low, kind of simple as that. Often in general, they're circular structures, and air converges on the middle. So if we look at an operational map, now they're more complicated than this, of course, got more going on, but this is in general what you'll see sitting out. If we pull up an operational map with the current analysis, we'll see several of these out in the Pacific right now. And they're these circular structures. So air is moving from the outside in towards the middle. But when we get north and south of about 5 to 10 degrees from the equator, Coriolis effect kicks in. And so air isn't free just to move straight to the middle. It ends up getting deflected to the right. And so it essentially, I mean, farther up in the atmosphere, it will parallel, just about parallel, the lines of pressure. As we get down towards the surface, friction, there's more friction with the surface. That tends to reduce the effect of Coriolis, and we get the winds kind of just crossing the isobars back towards the center of the low. Anyhow, but we get convergence at the middle of the low, and we get rising air. Rising air is air that's cooling off, air that's cooling. The dew point temperature is cooling down, or the dry bulb temperature is cooling down to dew point. Once that happens, air condenses. Once it's condensed, it releases a whole bunch of latent heat. So the air, the parcel of air gets warmer and wants to continue to rise. So water vapor really is the fuel for storms. Right. So clouds form, we get precip. We also get, like I say, this tendency to continue to rise. So basically we get bad weather. So are all storms the same? No. Here is kind of mugshots of two strong storms that kind of represent the two main types. Tropical cyclones, which you've already seen, and they're called by different names in different basins, or an extratropical cyclone. And this is what we get. We don't get tropical cyclones here. On the East Coast, they'll get the odd one. And when I lived in Halifax, because I did work at Bedford Institute of Oceanography on the other coast, that's when Hurricane Juan came through. And we lived right at the entrance of Halifax Harbor. That was 2002. And that storm came ashore with tropical symmetry and spiral bands and so on. We'll talk about the structures of these two storms in just a minute. In what was a very unusual event. We just had Frida now, just earlier this year, the same kind of thing. It came ashore as a tropical system. But that doesn't happen here. And I'll tell you why in a few minutes. But these are the two main types of storms: tropical, extratropical cyclones.
Excuse me, is there ever a storm that counter rotates in the northern hemisphere?
Only yes. So the question is, can you have a storm that does not go counterclockwise in the northern hemisphere? And the answer is yes, not at this scale. At the scale of a tornado, what's called the mesoscale. So there are tornadoes that have been observed to rotate clockwise, but you never at this scale. So yeah. And that's right. In the southern hemisphere, storms rotate in the opposite direction. Yeah. Okay, so if we compare them, tropical cyclones, hurricanes in the Atlantic Basin, typhoons in the Western Pacific, Bay of Bengal, and places like that, they just call them cyclones. They get names, we like to name them. But they're all the same type of storm. So they're all tropical cyclones. In the Pacific, they tend to be a little stronger just because there's a larger area over which they can power themselves up. They feed directly off of warm sea surface temperature. And that's why whenever you see the news about one of them, they'll always talk about these storms making landfall. As soon as they make landfall, they immediately start to degrade. You will never hear of a tropical cyclone forming over a landmass. That's just not how they work. They depend directly on water, on moisture that they're drawing up directly from underneath the storm. So they need that very warm sea surface temperature above 28.5 degrees Celsius. And that water is evaporated directly off the ocean surface and right into the storm. As soon as they hit land, that's cut off and they start to degrade. They're still very powerful, but they do start to degrade. They need a barotropic environment. That just means that the jet stream, which is a ribbon of fast moving air at high altitudes, flows over the mid latitudes, can't be present The jet stream destroys tropical cyclones. It just pulls their structure apart. You have a barotropic structure in the tropics. Don't get into that too much. They have a symmetric structure, as you see. They have almost that pleasing look, that bullseye look. It's white with that little eye right in the middle. That's a warm core. That means air is descending in the middle, warming up, and that's why it's cloud-free. So air rises all around the system. Most of it flows out at the top. Some of it flows to the middle and will actually sink. And the wind does cool down. There are some really interesting YouTubes where the storm is raging and then it gets quiet and then it picks up again, the winds from the opposite direction. They also have spiral bands. So if we'll look at the structure in a sec, but if that white part that's forms the circle around the eye, if you could just peel that back, that's basically like a layer of cloud, cirrus cloud, and it would reveal some spiral bands of basically thunderstorms, heavy thunderstorms. And so like when the storm came over us, there were periods throughout the night where the wind and rain activity would increase and then it would fall back off, increase, fall back off, as successive spiral arms made their way over us. The formation pathway is something called an easterly wave to a tropical depression, defined by wind speed, so 30 knots, tropical depression, tropical storm, 45 knots, tropical cyclone, more organization still, 60 knots. That's the threshold for tropical cyclone. But to be sure, we can have hurricane force winds without having a hurricane. You know, we get that around here a fair bit. We'll get winds that exceed hurricane strength, but there's not a hurricane offshore. And I'll show you this, like where do they typically go? I'll show you that in a sec. Extratropical cyclones, they tend to just be called, storms. We don't name them because really there's so many of them. Some regions have a specific name. So a certain type of storm that moves up the eastern seaboard will be called a nor'easter. These storms do not form in the tropics. So these are creatures of mid-latitude, just like tropical cyclones don't form in the mid-latitudes. These ones, the storms are almost opposite to each other in how they're organized and how they operate. Exotropical cyclones, they want a temperature gradient. Tropical cyclone wants everything the same, temperature all the same, just nice and warm, winds the same all the way up in the atmosphere. But an extratropical cyclone needs a strong temperature gradient. They typically form at the boundary of what's called the polar front. The jet stream sits above the polar front. And that's basically, you can imagine in the wintertime, the Arctic is cold. And then the polar regions are really warm. The polar regions, or the tropical regions, don't tend to change that much in temperature over the course of the year. The Arctic does quite a lot. In the winter, it's most extreme. So we tend to have a cold dome of air over the Arctic region. And then a fairly strong frontal boundary. The air doesn't grade smoothly from cold to warm. It doesn't really mix because it's different densities. So you've got a fairly distinct boundary between cold air and warm air. That's the polar front. And just above frontal zones, for dynamical reasons, we tend to get a flow of strong air above it. And in the mid-latitudes, that's the polar jet. But this temperature gradient, these storms tend to form along this temperature gradient. And they'll form where we have a cold continent, warm oceans, such as the eastern seaboard of North America, where we've got the Gulf Stream offshore, cold continent in winter, and in the spring, that's where nor'easters tend to come from, or warm cold ocean current. So who knows what the equivalent of the Gulf Stream is in the Pacific? What's the name of the current out in the Pacific that's basically the equivalent of the Gulf Stream? Everyone's heard of the Gulf Stream, but we don't live in the Atlantic. Huh? The Kuroshio. So the Kuroshio current is, like I say, it flows up the east side of Asia out across the Central Pacific. And so that also forms a warm, cold gradient. And storms can form along there. Don't worry about this. So these storms, and I'll show you a picture of this, draw their moisture in. So they don't depend on vacuuming up moisture from an area directly underneath them. You know, we think about blizzards on the prairies in the middle of winter. Well, there's no warm ocean underneath Saskatchewan in January, obviously. So they are drawing their moisture in. The most recent theory about how these storms work, and there have been a succession of theories over the years, starting with the Norwegian model, then the Chicago school, and then one of the more recent ones is this idea of conveyors, where these storms pull air in from different, there are three main conveyors for these storms. They pull air in from different directions along these conveyors. So they're able to move warm, moist air in from distance to power the storms. So a storm in Saskatchewan in the wintertime is getting its moisture probably from the Gulf of Mexico via a warm conveyor that's moving right up over the States. Baroclinic environment, that just means a strong temperature gradient like we just discussed. They're asymmetric, so they don't, like we just saw with the picture, they tend to look like a comma in, like if you look like on a satellite picture, they look like a comma. They've got this cloud shield that extends down, that's the cold frontal zone. And then they've got a dark area underneath it, and that's what's called the dry slot. And that's another conveyor coming in, cold dry air that moves in behind it. Right. So just one point. Unlike a tropical cyclone, an extratropical cyclone to become really powerful needs the upper air engaged. It needs the jet stream above it to be exhibiting certain patterns that will allow the storm at the surface to grow very strong. So just a cross-section view, there's a tropical cyclone, hurricane. There's that cloud layer, which you can peel off and you can reveal these rain bands, this rain band structure. This is a side view, of course. But if we look at it from above and peel that cloud layer off, it looks like a pinwheel, basically. And that's why, I don't know if you ever look at the news, sometimes you'll see tornadoes, a whole bunch of tornadoes get reported with a tropical cyclone, and that seems a little strange, but it's these powerful thunderstorm cells that are generated with tornadoes. This is the extratropical cyclone. This is the conveyor model. This is, I mean, obviously a schematic, but there's the center of low pressure. We've got our cold front that sweeps to the south. And there's the warm conveyor drawing the moisture up. And so as soon as the air rises, remember we talked at the beginning, air rises, it cools, condenses, clouds, rain, that kind of thing. So there it is coming in from the south, rising. There's another cold conveyor that comes in from the east, providing more moisture. And then this dry air that comes in behind it. We don't tend to get this as much here, but just one sec. If anyone who's lived in the east, like in Ontario or something like that, or Quebec, you get a cold front passage in the summertime, and we can go from air that's pretty moist and humid and muggy to air that's quite cool and dry. It really becomes quite refreshing on an August day, and that's a cold frontal passage where you've got a strong temperature gradient over the cold front. Is there a question?
How good are scientists at predicting that being developed? Like,
Extratropical
things going on. Oh, geez, it's going to turn into a cyclone.
That's a huge topic in itself. The answer is really good. The weather forecast models. So the Meteorological Service of Canada, with whom I work out of Edmonton, and our provincial emergency center here, one of the forecasters here. Meteorological Service of Canada, the Prairie and Arctic Storm Prediction Center, we've got 6 centers across the country that do prediction services, that issue the forecasts that appear on our phones. We are Prairie, or we are Pacific and Yukon. I tend to work with the Edmonton folks because they cover the majority of the Arctic. They will issue the forecast. The forecast starts its life in Dorval in Montreal, where Met Service of Canada has their main computer center, and they operate a huge model, a computer model of that captures sort of the fluid dynamics, the thermodynamics, and so on of the atmosphere system at a global scale. And this is their forecast prediction system. And so this model, every 6 hours, will be what's called initialized with a bunch of real life observations from satellite, from the weather balloons, from stations, from ships, as your ship sitting out there, from aircraft, whatever data they can get to say, this is what the world atmosphere looks like right now, and then go for the next 10 days. Sure, there you see a little storm out in the middle of the Pacific, what's going to happen to it over the next week? And the model will do that to the best of its ability.
The warning of storms, like 10 years ago, nobody warned anybody about storms. Now it's a big event, right?
Well, that's right. And that's because we are getting quite good at it. I was talking about this yesterday. I think that there is a difference in forecast success for us versus the eastern part of the continent, because there's a whole huge amount of data that the model can utilize over the North American continent. But for us, because the systems are moving from the west to the east, for us, we've just got the empty Pacific. So forecasting is a little more challenging here than it is for the east. It's also more challenging in general in the winter and in kind of the mid-latitudes, just because you can't get everything into the model. And that's why that's why we don't have forecasts issued for 30 days, 40 days, 2 months. Like nobody would ever predict, well, in February 7th, there's going to be a big storm that will hit here. We can't do that. That's one thing we definitely can't do. 1 week out in the winter in the mid-latitudes is all you're going to get. And that's why Environment Canada forecasts only go out a week. But yeah, for over the next couple of days, it's pretty, it's pretty darn good with the larger scale stuff. Okay, are there other types of storms? Yes, I'm not going to worry too much about them. There's a strange creature called a polar low that occurs only in Arctic regions. And then we've also got something called mesoscale convective systems, which are large, almost blocks of thunderstorms. They tend to call them supercells. These are creatures of the plains. We don't get these here. We don't get polar lows here, so don't worry too much about them. Okay, so the formation regions and tracks. So where do these systems form and where do they go? Not going to worry too much about this. I'll just show you the plots. Told you this. So in tropical cyclones in the Atlantic, this is how they go. Form here. So like we said earlier, the progression is something called an easterly wave, which is this disturbance in the atmosphere that is the progenitor for what could become a tropical cyclone. And what's interesting to this question, can we predict them? One thing that we can't do is you'll get, for every 10 little easterly wave that comes off of Africa, one of those will become a powerful tropical cyclone that say will impact the eastern seaboard or the Caribbean or somewhere. No way of knowing which one. So they track very closely these little disturbances. And if you go to the Joint Typhoon Warning Center in Honolulu, you'll see they're monitoring even these little tiny things because they're not sure which ones are going to evolve.
Do they evolve between Florida and Nova Scotia? Can they evolve?
Well,
they do it in the Caribbean.
They can, wherever they've got warm enough water. So if we have warm enough water, there's a potential, yeah. If it's not already a tropical cyclone. Once it's already a tropical cyclone, it has a certain amount of, momentum. It can move beyond, to sea surface temperature that's 27, 26, that sort of thing. Actually, what happened with Hurricane Juan, Halifax, so we have the Gulf Stream that comes up, And we get eddies, warm eddies that will kind of rotate off of the Gulf Stream. And Hurricane Juan, basically Bermuda's, I don't know, kind of around here, it formed north of Bermuda and then just made a beeline for Halifax. It was like some punishment sent against Halifax in Nova Scotia. And it was category 1. That's called the Saffir-Simpson scale, and you often hear these different categories for the storms. The categories are defined in different ways by central pressure, by wind speed, even by storm surge for some areas. But at any rate, it was category 1 according to wind speed, making its way along. And then just before it reached Halifax and Nova Scotia, it suddenly amped up to a category 2 and then hit. And the reason it did that is it ran over a warm eddy, just an extra burst of warm water that kicked up its power, and then it hit.
So I only asked you that question because I worked at BIO too.
Oh,
I just
okay.
wanted people to understand that science is science, and we can't predict everything.
Oh, yeah, no, that's definitely true. And one of the things that we work with in the Arctic, like between Edmonton and some of the communities, is what the forecasters don't get. Like, the forecasters will get a large extratropical cyclone, no problem. They know where it's going and what its life trajectory is going to be for the most part. But what the smaller the scale, the actual forecast has to be, that gets harder and harder. So when you're in the community and you'll get a forecast for, oh, it's going to be sunny today, what people at Edmonton don't know is that there's a crack in the sea ice that's just formed and it's pumping moisture into the air. And instead of a nice sunny day, they go down in snow squalls. And so the local scale can be the hardest to actually predict. But that's where people are. And so people say, oh, forecast didn't work. but they're getting the large scale things really well. And yeah, but yes, yeah. I mean, and with tropical cyclones, like we were saying, they reach landfall and they start to degrade, but they're still a very powerful system. And I think it was Camille in the 60s that made its way all the way up to Toronto and ended up killing 70 people and flooding events too.
Yeah.
And resulted in the creation of the Humber River Valley flood control system and things like that. So they're still very powerful systems.
Here too.
We use buoys for wave actions too, as part of that.
Yes, yeah, on the Scotian shelf, Hurricane Juan was measuring waves offshore of 75 feet. Yeah. Yes, yeah, very much so. Yeah, they're a critical point of information. Like offshore of us is La Perouse Bank buoy, which you guys probably know about. And that's, yeah, an important data point that we have for waves and other atmospheric parameters. The Pacific is much busier just because there's so much more area over which these things can form, get strong. It has a much greater proportion of these the heavy category storms, category 5, category 4, and so on. Yeah, it's just a much larger.
Japan's right under the center of that.
Japan down here.
Yes, Japan's right here. Actually, Guam is right buried in the middle
Indonesia.
there. And one of the things we did in Hawaii was have a look at a typhoon that had hit Guam, and it had it had caught the people in Guam off guard, and the forecasters were sort of wondering, like, what went wrong. And they came to the conclusion that the people in Guam, they get hit with tropical cyclones every year. And it's a pretty, they're pretty calm about it. So only if it's a really powerful tropical cyclone, they get worried in any particular way. So, and so this storm, the way they forecast is they'll show the track of the storm. Where do we expect it to be over the next couple of days? And at that time, this is the early 90s, they didn't include what's called a probability cone. a storm like this, you've got it at one location. Is it going to follow this precise trajectory? Well, this is the trajectory of best guess, in a sense, not guess, but our best informed opinion is that it will follow along here. But is there a chance it could move 10 degrees to the right? Sure. 10 degrees to the left? Yes. And that probability increases the farther from now you get. So that's called a probability cone. That's a standard feature on tropical cyclone forecasts now, but it wasn't then. And so people, I think, saw Guam, their home, and they saw the line going off to one side and said, oh, yeah, that's right. So we're not going to worry about it. But they kind of got caught out a little bit because it didn't really miss them. And they weren't, even though with all the experience they have with these systems, they still weren't kind of integrating the idea that, well, there's variability in the projected track. So, okay. Right. So coming on to extratropical cyclones here, they also have favored formation regions. And one of them is here. There's the Kuroshio current. So that's the center of, this is a plot showing where extratropical cyclones form, not necessarily where they're going. So we get a lot of formation here. We get a lot of formation off the eastern coast of Asia, just like we get a lot of formation off the east coast of North America. That's kind of the Gulf Stream. So there's a lot of activity here. There's a lot of formation that occurs behind mountain ranges as well, for reasons it's called lee cyclogenesis. Don't necessarily want to get into that. That's what's going on down here as well.
How would the volcano in Hawaii affect this?
The volcano,
Would it warm the temperatures?
not at the right scale. I think of volcanoes as more introducing particulates. Water vapor water won't condense. This is getting into a subject called cloud microphysics, but water vapor, if you've got a perfectly clean, you can imagine a little box, if you had a perfectly clean atmosphere, no pollen or smoke particles or anything in there, water vapor does not tend to condense until it gets quite cold. It has to be very, very cold, way below the dew point for it to form, water vapor to form. So water vapor, or liquid water drops, sorry, to form. Water vapor likes to condense onto tiny particles. And so if you introduce more particulates into the atmosphere, you can sometimes get haze starting to form, not at 100% relative humidity, but like at 90% sort of thing. The volcanoes effect, the real effect, I think, of powerful volcanoes is, yes, to introduce particulates. It's not so much a weather phenomena as a problem for like aircraft engines, which don't like to ingest silica-based sand.
We have volcanoes
around here.
And I was wondering if the power could it cause a cyclone,
Yeah, it's not, because these storms work on temperature gradients, it wouldn't necessarily do that. I think it would have to be a really big volcano, and then we'd be worrying about other things.
Yeah.
Large enough to do that, yeah. So just some research work that we've done. That's another PhD student I had, looked at variability and patterns of storm tracks in the Northern Pacific. And this is the sort of thing he was working on. So looking at different seasons, so DJF, December, January, February, March, April, May, June, July, August, September, October, November. I mean, in the climatology world, they like to cleanly break out these different seasons. And this is what's called genesis density, that's what he's called it, but it just means where do the storms tend to be forming? And it shows how how the patterns change over time. You know, winter, we get a lot more activity than we do in summer. And that goes back to what we were talking about before, where we have a stronger temperature gradient in the winter. So in the summer, it warms up quite a bit, of course, in the Arctic. It approaches temperatures farther south. We don't get that much of a gradient. We don't get that much of a reason for extratropical cyclones to
Have you
form.
found that global warming has affected the Arctic as far as storms go?
Yes, definitely. We tend to get more storms moving into the Arctic region. Yeah, for sure.
But that's a prediction or?
No, that's a fact. Yeah.
Okay.
Yeah, that's, these are hitting a lot of topics here. That's good.
Well, I've read quite a few times that the frequency of storms, of course, follows a statistical distribution.
Mhm.
But on average, averaged over multiple years, the number of storms and the intensity is about the same as it's always been.
That's true. Yeah, no, that's true. But where they're going is changing. Because,
That's the prediction.
no, that's a
Where are
fact.
they going from where they,
That's a fact,
from
yeah.
previous events? Are they going further north?
Yes, and the reason for that is the jet stream is exhibiting greater variability now than it was in the past. You know, so in fact, if you get into the IPCC, and a governmental panel on climate change, the predictions there, they'll ascribe levels of confidence, how certain they are in different types of predictions. So temperature change, yes, absolutely. But changes in extratropical cyclone activity, that one's harder to pin down, because if we warm up the polar regions, we reduce the energy gradient. And if these storms are forming because of this energy gradient, well, we have less reason for these storms to form. So there are like thermodynamic reasons for the fact that we don't necessarily see more of these storms, but the jet stream over in the past has tended to be a little more, it just kind of runs east-west. Now we're getting more waves in the jet stream. When that happens, if we get a wave pattern that kind of goes up into the Arctic, storms will tend to form along on the jet, along the polar front, and move with the jet into that region. So we're definitely getting more storms going into different places.
So have you noticed the ice melt?
Absolutely, yeah,
So when do you think we'll be cruising through the Northwest?
not for a
Passage?
long time, not for a long time.
Has it raised water levels in the ocean?
Melting of sea ice?
Yeah.
No, because it's already in the ocean. Yeah, the only melting ice that raises sea level is terrestrial ice that's melting and moving into the ocean.
Glacier, we get a lot of that.
Right.
area.
Yeah. So this is just showing where storms come to die. And it shows that kind of the Gulf of Alaska, our coast is kind of the graveyard of North Pacific storms. And the reason for that is these storms are surface features, and the topography stops them. They don't move over in the forms that we recognize. They don't move over the mountains. Yeah, where they track, where they're most intense. So he did a whole bunch of things. Okay, I'm going to worry about that. Yeah, and then just more recently, yeah, so we learned a lot of new words last year. A bomb cyclone that's got people excited. A bomb is just a storm that drops more than 24 millibars in a 24-hour period. But it sounds dramatic. It's just a rapidly intensifying extratropical cyclone. But yeah, October 25, we had the bomb.
Who thinks up these new names every few years?
Atmospheric rivers.
Well, it's
Is that a scare tactic or something?
Well, it's
Yeah.
sort of interesting. So here, so this is an operational chart. And what do we call these fronts, right? Well, it's like a battlefield. Well, the first theoretical conceptualization of extratropical cyclones came out of what's called the Norwegian School out of Bergen in Norway during World War I. And they were, I think that was the thought that was in the air at the time. And so they called them fronts, just like on the battlefields of Europe. So atmospheric river. Well, actually, let's go to, I think we're running low on time. This is just showing that storm from last October and then how the jet stream helps. So here, atmospheric river. So that followed a few weeks later. An atmospheric river, all right, so this is at 700 millibars. So this is at about 10,000 feet elevation in the atmosphere. This is what the pressure pattern looks like on right around the time October or November 13 of last year. And so what we've got, that's low pressure, that's high pressure, and like we talked about earlier, the wind is moving along the pressure gradient. Without Coriolis, it would go from the high to the low. But because of Coriolis, it ends up moving along the lines of pressure. There's Hawaii, there's us. So the winds are moving out of the southwest. And then if you look at moisture, so this is what's called columnar precipitable water, but it just means if you take all of the water vapor in the atmosphere and condense it, that's how much rain you would get in kilograms, or how much moisture you'd have in a bucket or something in kilograms. So it just, the more the blue and purple, the more moisture it is. So that's the intertropical convergence zone, tons of moisture down here. But here we can see what that pressure pattern with the winds reaching down to this area have done. They've pulled up this ribbon of moisture, and basically it's driving it into the west coast. That's an atmospheric river. And you can see there are different areas where that's happening. Like there's another similar feature in the South Atlantic. Same exact thing. Same type of thing up here. So we've got a low here and a high here. And this happens not infrequently because we often get, like we just saw from the earlier plot, where do storms come to die? Where do these low pressure systems come to die? Well, the Gulf of Alaska. And then what do we have down here, keeping California sunny all the time? A great big high pressure zone, the East Pacific High. So we often have high and low, just like we saw here, setting up this very favorable pattern, very favorable flow pattern to pull moisture from the tropics into the West Coast. In the past, California has seen the brunt of this. It wasn't necessarily something we talked about that much, although I'd be interested to see a study that tried to find previous occurrences here. Sorry?
Is it creeping north?
Yes, yeah. And so there are, I was at a panel with the provincial government, this is some years ago, where they're kind of getting worried about this. I mean, for very good reason. We saw what happened last fall. Exactly this problem. And the reason they're creeping north is we're now getting a more variable pattern in the jet stream.
Does that affect rainfall for California too?
Yes, it would, to the extent that if they're not getting this flow, if they're not getting it, someone else is. Yeah. Just like with storms, right? There aren't necessarily more storms, but where they're going is changing. Where they're tending to travel is changing.
No, I've heard, I don't know if it's accurate, that this is the third year in a row that the Pacific Ocean has been colder than average. Is that showing, is there less storms, more storms, say storms? Or when they're talking colder than average, they're talking about maybe a 1/10 of a degree or something?
If it's enough that it's kind of making it out, outside of the science realm, it's usually a couple of degrees. I mean, I'm not sure offhand. I'd have to have a look. What differences in sea surface temperature do is they will change, not necessarily where storms like the actual formation of storms, but they're changing the zones of high and low pressure. This is how people have probably heard of El Nino. El Nino and the Southern Oscillation. So El Nino is an ocean pattern. Usually, if we go back, well, go to this plot here actually. What we have is the winds flow from the west, you know, in our area. Along the equator, they tend to flow from the east to the west. They sort of flow in the opposite direction to what we would recognize. And that tends to move warm surface water over to the east, or over to the western part of the Pacific. And around Christmas time each year, the winds, the trade winds, I mean, these are the trades will weaken a bit, and some of the warm water will come back. And people who've lived here have recognized this, and they call that El Nino, you know, the child, right? Because it's happening around Christmas. Every few years, every 2 to 5 years, the trades get much weaker or kind of stop altogether for a period of time, and we get a lot of warm water coming back. That seems like a local phenomenon, except that there's an atmospheric pattern that perfectly matches that, called the Southern Oscillation. And so if we increase the temperature of the water here, we are reducing the pressure, we're reducing the air density above it. So we're tending to create a zone of lower atmospheric pressure above it. And the atmosphere, there's only so much atmosphere, so it's a zero-sum game. So if we reduce pressure here, we have to increase pressure somewhere else. And that's called a teleconnection. And so that's why when we have El Niños, a strong El Nino or a weak El Nino occurring, we can have the opposite called La Niña. Those patterns, even though starts with an ocean phenomena in the southern hemisphere, by means of these atmospheric teleconnections, we increase pressure here, it has to decrease here, it's increasing over here. These teleconnections make their presence felt in different parts of the world. So during a La Nina period, we tend to have a zone of higher pressure offshore, and that will change. That means we tend to have a colder winter. Not so much because it's affecting the formation of storms, but it's affecting where the storms are going.
So what people want to know is next summer, will we have a good fishing season? Because we don't have a lot of storms.
So that's an interesting question. Yeah, well, so, you know, we mentioned the Meteorological Service of Canada and their forecasts, you know, they go out 7 days. The IPCC, with its forecasts, I mean, these are climate projections in our forecasts, but they go out 40, 50, 60 years. Well, what about this middle zone? What about a seasonal forecast? They do exist, but their operation is tied to things like El Nino and the Southern Oscillation. So there's been a lot of work over the years to try to say, well, when El Nino cycles up and then cycles down, cycles up, cycles down, how do those cycles affect our weather? Right, do we get more storms or less storms in the summer when we have a strong El Nino? To the extent that we can link the two together, that allows us to use El Ninos as a means to offer up longer term rough predictions of how a season down the road is going to shape up.
What's your personal prediction for next summer?
Oh, I wouldn't even dare to guess.
We want to.
Yeah, I wouldn't dare to guess. Yeah.
Do you have a comment on today's weather in central North America?
Central,
Supposedly it froze in Los Angeles last weekend. And Dave's, there's a foot of snow coming to Lake Manitoba today or tomorrow. And it's supposed to be in Nova Scotia, where this guy's from, on next weekend.
oh, well, I heard about a strong system that's
Come
dropping
from the Gulf of Mexico to
tornadoes.
Lake Manitoba.
Yeah, well, it would be probably an extratropical cyclone. I haven't looked at it, but
Okay.
but yeah, it'd probably be an extratropical cyclone that's that's, like I say, drawing the moisture up and,
Is it bringing the moisture from the Gulf of Mexico and dumping it in Manitoba?
that's right, yeah.
Those
Essentially,
conveyors are getting-
and some of it from the Atlantic, but yeah, no, these storms pull it in from far away, so, yeah.
Not in the wintertime, I'm keeping my doctor's shoes in the winter.
Yeah, other questions?
It's interesting to see the symmetry between the northern and southern hemispheres.
So we go back
Yes.
to the farmers, the home.
Farmers, yeah, look for the caterpillars, how much fur do they have, yeah. That's right.
And there was always, if this storm is going through the continent today, there's been storms this size.
Oh, well, that's, yeah, okay, that's a good question, or that's a good point. Okay, we've got other stuff. I don't have a good, so another difference between tropical cyclones and extratropical cyclones I didn't point out is their size. We think of hurricanes, tropical cyclones as big, powerful storms, and they're very powerful, but they're not particularly large. They might just be a few hundred miles across.
Well, this looked like it was about 2 states wide going through the central plains, the northern plains of the state.
That's right, yeah, an extratropical cyclone. So I've seen satellite images that have the low more or less centered over the Great Lakes. The cloud shield extends up to James Bay, and the cold frontal zone sweeps right down over the eastern seaboard into the Gulf of Mexico. So the storm is covering the majority of eastern North America. So they can be huge, and that's not a climate change thing. That's just the nature of these types of storms. So yeah, you could easily be getting a storm that's along the cold front is dropping tornadoes in Oklahoma. I actually lived in Oklahoma as a kid. So my dad's in the Air Force. Could just, the same system could be dropping snow in central Manitoba. Yeah. And the tornadoes will be forming along the cold front, because that tends to be, the cold front of these systems will be an area where there's the lifting is fairly strong and active. And you can often get fairly powerful thunderstorms that will result in
Yeah, like it
tornado
looked pretty
activity.
nasty. The national, I just happened to have the CBS on the morning for a minute. and Got the weather forecast. It was coming from the Gulf of Mexico. Well, from the warm to the cold to the and back and forth, like it's gonna make ice in some places and it's supposed to, then you go to CBC and it's gonna drop a foot of snow in Manitoba.
Yeah,
It's a good place for it.
Good point.
I don't know whether that's the right answer, but anyway, my family are all
Are you wrapping up or is that?
yeah, no, that's it. We're kind of drifted into comments. Although I'll pull up, if people are curious, we can pull up the current satellite image and see what's going on.
Yeah.
Sure.
But
How long, you must have been with GSC, were you?
that's correct.
Yeah, I managed BIO when I was there.
We managed it. Oh, okay.
2004, I was there for 10 years
Oh, okay.
and then I went with the Coast Guard.
Okay.
Yeah,
Oh, wow.
so you look familiar, so we must have crossed paths.
Could be, yeah.
Most of my staff would have been wandering through, looking
Well,
after all the buildings.
Here's my
Coast Guard,
Coast
yeah,
Guard hat.
yeah. You weren't in, were you on the ships?
No, but I've had a grad student go out on the Saint Laurent, the Wilfrid Laurier, and then on the Finnish icebreaker as well.
Yeah.
Because we do work with the Canadian
used-
Ice Service.
I used to coordinate a lot of the fisheries joined with Coast Guard or Coast Guard joined with fisheries, depending on who you were.
Yeah.
And then we got rid of all the fisheries ships. Fisheries had their own fleet and then they all became Coast Guard vessels. And there was a need to coordinate the activities because interesting enough, a captain of a ship doesn't like to have holes drilled in the bottom of it.
Yeah.
And a lot of
You
the,
want to put instruments on.
yeah.
I just had a question about your plots. So 2005, why so far back? Are there more current plots? Like were dated 2005.
Oh,
So for your plots, Atlantic versus Pacific and the tracking.
oh, I see. Yeah, there's, I mean, they cover so many decades that it's indicative. It wouldn't really change. Yeah, no, I just haven't bothered.
This is
updating.
part of going to the search group, isn't it? So that's,
Pardon
this
me?
is part of presentation, is part of research work from your students, isn't it? Huh?
Some of it, yes, yeah,
so
that's right.
what we're saying, it's
Yeah,
stuff from the past.
yeah, yeah.
As senior fishers, we look out the window before we go out.
Well, that's always the best.
Anyways, well, thank you very much, David, and we have a little token of appreciation.
Oh, thank you.
And we really enjoy the speaker that we can draw from the University of Victoria. We have used them quite a bit. So,
Okay. Yeah, and I apologize for the late
No,
start.
that's
Glad you
okay.
hung around.
no, you can tell we're interested in this. Interesting, we had a presentation, part of the club had a presentation on eelgrass and how it affects,